Chapter 9, Introduction to the T-Statistic, Part 5. So as I indicated in the previous video, I'm going to walk you through a confidence interval example using 90% and then 95%. And then I'll also discuss the effects of different variables on the confidence interval, or how the implications of its accuracy in terms of the range and percentage. So as we saw in the last example, we identify the percentage. In this case, it's going to be 90% confidence interval. We're calculating the anticipated mu for the amount of time spent looking at the attractive face for these infants, given the ability to access all infants in the population. We're going to use the sample statistic, the sample mean, as the center of our prediction, and then find our t-value and our estimated standard error, which has already been calculated. So I'm going to replace the variables that we already know, and they include the mean, which was equal to 13, plus or minus. The t-value is what we're going to find in our t-table, and we know that the estimated standard error is equal to 1. That has not changed. So visually what we're doing, again, is calculating the population average for the amount of time spent looking at the attractive faces, using the sample mean as the center of our prediction. Again, this is representative of mu attractive. And we're going to partition off 90% in the center. So again, the last example was 80, so 90 we should stretch out a little further. And now this center value area has increased to 90. What's left over is 10%. So we're going to use that 10%, convert it to proportion to use our t-table. So we divide by 100 and we get a proportion 0.10. And now we're going to find out what that t-value is equal to, given the parameters of 90% confidence and degrees of freedom. Again, degrees of freedom was equal to 8. So here's our t-table. Again, as I indicated previously, the process of finding the confidence interval range is always applicable to a two-tailed process. So we'll always use the second tier. We're looking for 0.1, the proportion, and degrees of freedom equal to 8. So we're going to see where those intersect. And we find that t is equal to 1.860. So we can use that in our equation. So our t is equal to 1.860. And again, we're calculating a value below the mean of a sample mean of 13 and above. So if we add 1.860, again, because the product here multiplied by 1 is simply saying we're taking 13 and moving out an additional 1.860. So that would place us at, in our calculators, or just do a quick easy math, 14.860. And then on the lower end, we're saying we're taking 13 and subtracting that product of 1.860. So that would give us, in our calculators, we should get 11.14. And now what we're saying is that we're 90% confident that if we had access to all infants in the population, the average amount of time they would spend staring or looking at the attractive face is equal to 11.14 seconds, and ranges all the way up to 14.860 seconds. So again, the percentage of the confidence has increased, but you should note that the accuracy or the precision of our estimate has decreased. So when it was 80%, just as a reminder, the range was on the low end of 11.603 all the way to 14.397. That was from the previous video example. And so we increased our confidence percentage, right? Now we're 90% confident. But notice the precision, that the range has increased, right? Because the center portion has increased, so that range has expanded. So if the range of our prediction expands, hopefully you can understand that the precision or accuracy of our prediction is compromised. It diminishes because now we're saying that it falls within a larger range of values, but our percentage of confidence increases. It increases because we have a better chance of falling within that range. So I just want you to note that relationship, that as the percentage of confidence increases, the range, right? The range increases as well, but that is also understood as the precision or accuracy of our range is somewhat compromised. So that decreases. The precision or accuracy decreases as the percentage of confidence increases. And we'll talk more about that in just a moment. Now I want to walk you through the same example using 95% as the confidence interval, just to give you some more examples. Okay, so for additional practice, we'll use 95% as our set confidence level. In our equation, we can replace our variables. So again, we're anticipating what the true population average would equal if we had access to all infants. We're going to use 13 as the sample statistic to center this prediction, plus or minus our t-value, which is going to come from our table, and our estimated standard error, which was calculated previously, equal to 1. So now visually, we're talking about 90% confidence. So the center expands even further out. So we have 95% in the middle. It's centered at the sample mean equal to 13. Again, that's representative of mu attractive, right? Represents mu attractive. And what's left over is 5% in the tails. Again, there are two of them. We're going to convert that 5% into a proportion. We divide by 100 and we get 0.05. Now we're going to utilize our table to find out what that t-value is equal to in our equation. So again, we're always using the second tier because there are two values we're solving for, above and below the mean. There's 0.05. Degrees of freedom is equal to 8. So we see where those values intersect with one another. Should be lower here. So we get the value of 2.306 as the t statistic for this equation. So we can replace that now, 2.306. So that means we're adding that value to 13 to the right. So that would be 15.306, and we subtract it from 13, and that should equal 10.694. And now what we have solved is that we can say we're 95% confident that the true population mean, or the amount of time these infants spend looking at the attractive face, ranges from 10.694 seconds all the way to 15.306 seconds. Again, our confidence percentage has increased. Our confidence has increased, right, that it will fall within this range. But the precision or preciseness or accuracy of our prediction is has decreased because now we're talking about a much wider range than the example of 80% and 90%. But that's okay. You just need to recognize the consequences of increasing your confidence percentage and what that implies for the range of values and the accuracy or precision of the predicted value. So again, had we have access to all infants in the population, we are 95% confident that the infants would spend 10.694 seconds on average, anywhere from 10.694 seconds all the way to 15.306 seconds on the attractive face. And again, something to note, the null, the mu coming from the null was set at 10 seconds. So it's important to recognize that the range does not include the null. Again, the null would be slightly over here, right? 10, this is 10.694, and 10 would be to the left of that. If your confidence interval includes the null value, the mu that's reflective of saying there is no difference, then there's something wrong, because why would, think about it, if you're saying I'm 95% confident that they'll spend anywhere from 10 seconds to 15 seconds, if it includes the null, then you aren't really saying that there is a difference. So it's something that we'll talk about more, and I actually do illustrate quite a bit and in depth in the demonstration videos, the example videos for this particular chapter, and also in subsequent chapters of 10, and 11. So something to keep in mind. Your confidence interval should not include the null mu, the mu from the null. In this case, it was 10 seconds. And as our confidence percentage increased, that range increased, but again, still does not include the value of 10 seconds exactly. It's somewhat above that. So here's a slide just illustrating the relationship between these variables when we're talking about confidence interval. So confidence level desired. More confidence desired increases the interval width. And I just demonstrated that with those three examples, one in the previous video and the two in this video at 80%, 90, and 95%. So as our confidence percentage increased, the interval, the width of the interval increased as well. But recognizing that the precision or accuracy of our prediction diminishes, it decreases, because now we're talking about a wider range, but our confidence percentage is higher. Conversely, less confidence acceptable decreases the interval, so we have a smaller range. So again, the comparison of the 95% confidence interval example opposed to the 80%. 80% we have less confidence. Our width of the interval is smaller, but more precise, more accurate. So again, recognize the trade-off there. Next, sample size. Large sample is going to produce a smaller standard error of the estimate in the smaller interval. Again, smaller interval means more precision, more accuracy. Smaller sample means a larger standard error and a larger interval. So the larger interval means less precision. And again, this statistic or this variable is represented variability. When we're trying to precisely hone in on a prediction, we want less variability. So just kind of think about how these things are all related to one another. So larger samples produce lower variability and a smaller range of estimated values, a smaller interval. Smaller interval means more precision or accuracy in our prediction. Conversely, smaller samples produce greater variability and produce a larger range of values for our predicted mu. Larger interval is indicative of something that's less precise or accurate. And it's important to note that the percentage set for your confidence interval is strictly up to the researcher in the real world. For our purposes, those would be given values in the homework problems or an exam or quiz item. These percentages will be given to you, and now you know the steps necessary to find the calculated predicted population mu given the equation, and how to find the t-value from our table. So again, in the real world, the researcher gets to decide the confidence interval, recognizing the elements and consequences of larger confidence, smaller confidence in terms of the precision of your prediction. For our purposes, those values will be given to you. So at this point, we have walked through one hypothesis test from beginning to end using the four-step process and calculating the measures of effect. Now in the literature, you will see it cited, or the conclusion cited in a specific format. So we report whether or not the test was significant. Significant means we reject the null. Not significant, we fail to reject the null. Report the t-statistic value, including the degrees of freedom, as indicated here at the example. Here's just one example of what that may look like. And then we report the significance level, either p is less than alpha or p is less than 0.05 to be more specific. Exact probability is something that you could include, but I'll demonstrate exactly how you will see it in APA format and how you will see it illustrated in your homework problems or quiz items or exam items. So for this example, again, we begin with our conclusion regarding the null. So in this case, we did reject the null. Again, that was based on our t-statistic or critical t-value. All those things were demonstrated in the previous video. So we reject the null. Then we verbally state what that means in terms of the context of this particular research. So we could say that results indicate that the time spent looking at the attractive face was significantly different than would be expected if there were no preference. Again, what we're saying is that it's unlikely that if we took a sample of infants from the population that they would average 13 seconds staring at the attractive face if the null were true, the null saying that there is no preference. So now that's why we get to reject the null. The results indicate that the time spent looking at the attractive face was significantly different than would be expected if there were no preference, or if you can exchange that phrase to say expected if the null were true. Then this is followed by the notation necessary. So our t, we would say t degrees of freedom in parentheses, in this case was equal to 8. Our t statistic was equal to 3.00, followed by our probability statement. So the probability, we had conducted a two-tailed test with alpha set at 0.05. So we would say the probability is less than 0.05. In other words, there's less than a 5% chance that we would obtain a sample mean equal to 13 if the null were true. Again, what we're saying is that there's less than a 5% chance that we would obtain a sample mean equal to 13 if the null were true. The null says no preference, no difference. So we're saying that the likelihood that this sample mean of 13 would result if there's no chance is, no preference is very small. Therefore, it's supporting the idea that they do have a preference. And then we could include our measures of effect. R squared was equal to 0.5294, or we could include our t squared, our confidence interval, estimated D, which was equal to 1.00, or our confidence interval 80%. So we could say 80% confidence interval, and within brackets the range of that interval, which was 11.603, comma 14.397. Close the bracket, and then our period to end this concluding statement. Now, the R squared, estimated D, and confidence interval, all measures of effect size. And in the real world, the researcher would opt to just report one, not all three. But I would just want to illustrate how all of those would be included. Again, the researcher would opt to just report one of the three. And again, given the values that we calculated, they are all in support of rejecting the null. Again, our estimated D was greater than 0.8, which was considered a large effect. R squared was greater than 0.25, also supporting a large effect. And then our range or confidence interval did not include the mu from the null, which was 10. So again, that value is not in that range. So again, all of those statistics support rejecting the null hypothesis. So again, Results indicate that the time spent looking at the attractive face was significantly different. That's what we were testing. Significantly different than would be expected if the null were true. Or in other words, if there were no preference for the attractive versus the unattractive face. And then our supporting statistics would follow that statement and written in this manner. Now, I do want to point out that if we get to just a good thing to keep in your notes, if we reject the null, students always have problems with the probability statement. Then we would say the probability is less than our alpha, whatever alpha was set. If we fail to reject, the probability is greater than alpha. So keep that in mind. This is something of importance for your notes because students sometimes don't understand, and what they don't understand is, again, we're looking for something that has a very small probability of occurring if the null were true. Because what that indicates, when we see something that looks like this, that means that our value was out in the tails. If we see something like this, probability is greater than our alpha, that means it's in the center region, that we failed to reject the null. So again, keep that in mind, that if we reject the null, the probability statement will say that it's less than alpha. If we fail to reject, it's greater than alpha. Less than alpha means it's out in our t-statistic is out in the critical region. Greater than alpha means it's in the center common region of our distribution. And we'll end this video with a learning check to assess the understanding of the material that was presented. So let's consider the following. The results of a hypothesis test are reported as follows. T and then degrees of freedom equal to 21. Our t-statistic was equal to 2.38. The probability was less than an alpha set at 5%. What was the statistical decision and how big was the sample? So again, given what I had just discussed, when we see probability less than alpha, that means that we rejected the null. Again, our distribution, we set our critical region. Here means it's less than alpha, so we get to reject the null. So let's look at which ones say reject this. So reject the null, not reject, so we can eliminate those two. Next, we need to determine what was the sample size. So again, degrees of freedom is equal to n minus 1. So if this represents degrees of freedom, we would say 21 is equal to n minus 1. So n would equal 22. And that would be this one. So our answer would be B in this case. So you'll get some questions like this. Again, they'll give you a concluding statement, and based on your understanding of each of those values, you can determine whether you reject the null, fail to reject the null, and also identify what the sample size was for this particular research study. And let's determine if the following statements are true or false. First, sample size has a great influence on measure of effect size. Well, let's think back as to why we need measures of effect. We discussed in Chapter 8 the flaws of a hypothesis test using a t-test, or excuse me, a z-test. And the flaw was that the end results didn't necessarily give us a sense of effect size. And the reason why was z was equal to m minus mu divided by the standard error. Standard error was equal to population standard deviation over the square root of n. So we recognized that n had sample size had a great influence on our standard error, and the larger n values produce smaller standard error produced higher z-scores. So we wanted to eliminate the influences of effect size when we compute Cohen's d, r squared, and confidence interval. More precisely and more specifically, Cohen's d and r squared. So since those were created to address the negative influence of n, we would conclude that sample size has a great influence on measure effect, that is false. We're eliminating the influences of sample size when we calculate d and r squared. Next, when the value of the t-statistic is near 0, the null hypothesis should be rejected. So again, we have our distribution. T in the center is equal to 0, meaning that there's no difference, no effect size. So if we're near 0, that would mean we would fail to reject. We want our values to be very different from 0 out in the tails. So this statement would be false as well. When the value of a t-statistic is near 0, we would fail to reject the null, not reject the null hypothesis. And that concludes the lecture for Chapter 9. If you have any questions, please post them to the discussion board where these videos appear, or you can send me an email to clarify any of the information presented here.